Welcome everyone. My name is Nick Beavers, here from Cybernetics. Today we're going to cover particle analysis. We want to put a focus on quality control and how you can use deep learning automation for applications that can be challenging and that could potentially introduce errors into your quality process. Um, as I mentioned, I'm Nick Beavers, CEO of Cybernetics. I'm happy to have you reach out after the webinar with my contact information on the screen. Feel free to connect on LinkedIn. And I'm joined today by Tom Moyer, our sales manager, with his email on the screen as well. And hopefully today we can provide some useful information that will help with the topic we're talking about and provide some new information and some actionable guidance. If you don't know about Cybernetics, I just want to do a brief introduction to let you know that Cybernetics as a company has been in business since 1981, and we've been helping labs go from images to answers for over 43 years. While doing this, we've managed to work with our customers to produce over 150,000 publications, making us the largest independent software company, putting a lot of good peer-reviewed papers into the world for moving a lot of different industries forward. We're very proud of this and very proud of working together with companies to do so. We are based in Maryland in the United States on the East Coast, but we operate as a global company with employees and partners all around the globe. Really excited that by offering the solutions that we do in so many different locations, we have created a really great global community working together to go from images to answers every day. And if you'd like to learn more about us, feel free to visit us at mediasci.com and join us at YouTube at Image Analysis or even on LinkedIn at /Image Analysis, and lots of good content, information, and more about the topic we're covering today and many others, always being updated. We want to talk about the solution today regarding particle analysis, but we're going to do so as much as we can, providing guidance from a large variety of perspectives. Obviously, we're the creators of the imagepro AI software, and so for that reason, we are going to talk about how imagepro could address some of the problems that you might see in particle analysis quality control. And it is an AI-powered image analysis platform that is built for research microscopy and quality control and allows you to get stunning results, as we're going to hopefully be able to demonstrate today. One of the things about imagepro, and we'll talk about this a little bit later, that makes it unique is its ability to be an end-to-end solution. Whether you're importing images or capturing images, bringing them into the software, then processing them in some way to improve the quality of the image, measuring them, and producing high quality database results, and of course, always sharing that and reporting it out in some way, shape, or form. You're going to be able to get an end-to-end solution with this product. So just again, the introduction of who we are the producers of the imagepro software, and our most recent release is our imagepro AI version 11.1 product. What this does provide is material analytics at pretty much any scale. And because of this, we are able to work with magnifications ranging from very low magnification, producing electronic component analysis with stereoscopes and stitch scans, through materials cross-sections with polarized light, reflected light, material composition with wide field or confocal microscopy, and even transmission electron X-ray as well, and really moving all the way to the highest magnification for EM material microstructure. We work with SEM, TEM, and even FibSim. So generally what you're going to see from Cybernetics is this ability to work in a lab really with a lot of different instrumentation and for a lot of different applications as well. It really becomes a very flexible analysis platform to allow working in a repeatable environment where the software becomes something that you can learn and understand and easily train on, or really regardless of the type of analysis that needs to be done. So today we want to talk about Particles. We want to talk about the importance of particles and how we're going to reduce some of these errors. Before we jump into that, let's set the stage with what a particle is, because that will help us to understand what we're going to address. According to the ASTM standard, a particle is a discrete unit that can be distinguished and measured individually in the field of view, typically by differences in optical properties or morphology. The ISO standard says it's a discrete small object of defined shape and size, which can be characterized individually by physical, chemical, or biological properties. Both of these are pretty much giving you a very broad definition of a discrete small object, but that's very vague and it can be widely applied. And so for that reason, there's a lot of different types of particles. From the perspective of what we should cover today, let's see if we can look at first solid objects and solid particles that could be anything from a grain or a crystal that we found in metals or ceramics or polymers to powder-based particles seen in additive manufacturing, pharmaceuticals, or coatings, fragment or debris type particles where you're looking at irregular particles from breakage, wear, contamination, potentially dust residue, maybe airborne pollens or spores, or even biodebris. You could have spherical or microspherical particles that are used in calibration, medical devices, or even drug discovery, and even some type of fiber-based particle, something that looks elongated, glass fibers, asbestos, or something synthetic. Many different types of solid particles. You could even look at liquid or gas-based particles. You could look at something that would be a droplet, such as aerosol sprays, emulsions, or inkjet printing. We could look at kind of a non-particle almost, but acts and behaves just like a particle, which is the defects in coatings, voids in foams, or even different polymers that may have vesicles or bubbles inside them. So liquid or gas particles that are in some type of substrate really do have a huge impact, whether solid, gas, liquid, on the material that they're a part of. The impact of these particles is pretty substantial. It can create reactivity of dissolution rates in minerals. It can impact the rate of absorption and bioavailability in soils, stability and suspension, paints or emulsions, drug delivery, texture and feel of food ingredients, flowability of powders, viscosity of suspensions and slurries, packing density and porosity of ceramics, and even settling time of cement. Would be some kind of sea salt. All right, so what we're going to look at is all the different types of particles. We're going to have a lot of different methods for measuring them and the quality control of those measurements. And what we wanted to point out today was there's a lot of ways of measuring particles. There's generally three main ways, and things can be grouped in this way, where you have separation methods, ensemble methods, and counting methods. Generally, though, let's look at what is inside of each of those groups. You have things like mechanical methods. Obviously, you can take your particles, if they're powder-based or something, you can actually do a sieve, and you can very, forcefully work with your particles to group them into different sizes, or however you need to sieve them and actually create a distribution. You could have some type of sedimentation or centrifugal type device that would separate objects based upon their density or their size. Aerosol-based or fluid-based counters, where you're many different devices on the market where I can look at how particles are in a solution or how they are in some type of gas. And of course, I can also then use light or laser, and I can use these for diffraction, for scattering, for looking at how my particles look inside of this small sample that I may put into a system like the one on the screen. Last but not least is the microscopy-based measuring method. I'm using an optical light microscope, or I'm using an scanning electron or a transmission electron-based system, and I want to understand more than just how many particles there are, I want to learn a little bit more about them. And for that, let's do a quick comparison of why I would use each one of these techniques. If you're already in this field and you already maybe have one of these devices, this is going to be nothing new to you. You probably already know a lot about this. For those where it's maybe a little bit more new, a high-level overview of the comparison would basically say we want to use mechanical methods when we obviously have larger particles, anything from a few millimeters to, say, 40 microns. I'm not going to get shape information. I'm going to have very low detail, pretty much nothing in terms of understanding of the particles themselves. It really only works for mostly dry powders and granules, and it's a bulk analysis. The throughput can be high. Obviously, I can do this, with a lot of material, and I can maybe automate this, of course. My cost is going to be low. It's a very simple method. If I want to do a sedimentation or centrifugal type method for separation, of course, I can then work with smaller objects, smaller particles. The centrifuge is going to go even smaller. But again, I don't get any shape information. My resolution, maybe it's a little bit better than I would use with mechanical methods, but it's really going to work when these are in suspensions and some kind of liquid. And it, again, is a more bulk analysis. A little bit lower throughput. It's harder to have a lot of material used in these situations. So also automation is going to be more moderate. Cost will be a little bit more. Aerosols and fluid counters, again, can start to go into the nanometer range. I'm not going to get any shape information. I can, of course, look maybe in certain scenarios, look at the count and maybe a size bin. This is going to limit me to airborne and fluid-based. And okay, maybe I can get some count-based, sometimes some single particle, but most of the time this is also still bulk. I can go high throughput with these, and I can automate this fairly well. So your cost is going to be still around the medium to maybe high range. As you start to go a little bit further, we can get even smaller sized objects where we're looking at laser diffraction and we're looking at light scattering, and we can really get down to the nanometer, micron level. Again, no shape information. This is all about batch, just generally understanding size distribution. Good for suspensions, powders, emulsions, and it is a bulk process. High throughput, high automation, and cost, again, medium to high. And then last but not least is our microscopy-based methods, where we can get a pretty wide range. We can look at micron-based. Of course, you could also go even higher. You could go millimeter-based with some kind of stereo or standard microscope. But I can even do SEM and TEM and get down into the nanometer range. I can look at shape information, so I can start to understand morphology. I can actually look at high resolution, shape, surface, and texture. My sample can be varied. I can really just depend upon the prep that I do. I can look at just about anything, and I can look at single particle detail. Of course, this is going to be a little more challenging on the throughput side. And what we hope to show today is that it is about a medium, but with automation, maybe we could justify saying high here, and then automation potential, again, moderate to high. The cost is going to vary widely because it does depend on whether or not you're working with a very simple light microscope or an electron microscope, which of course would take even more skill as well and a little bit more training. Generally, our customers and the people that we work with on a regular basis, once we've gone through some training and we have a plan up in place where we can walk through and get a team up to speed, we really feel like this can be easily documented and reproduced and can be on par with a lot of the other methods. Microscopy-based is what we're going to focus on today, of course. That's the field that we're going to really put our emphasis on, and it is where you're going to get the resolution, the detail, and the accuracy and confidence that the particle analysis is accurate. So what are some ways to measure the QC? Well, obviously count, size distribution, affecting the flow and packing and all these, shape and morphology, which of course is going to influence whatever product behavior it's a part of. The surface texture is possible for adhesion, coating, reactivity, whatever it may be. And a big one, defect detection, wanting to understand and identify unwanted particles or irregularities there. So all this analysis that we may be doing for our particles does come when we're working with microscopy-based methods with a number of challenges at times. And what we're hoping to go through today is outlining what we see to be the most common errors the most common challenges, and trying to see if we can come up with a solution that overcomes these types of challenges. The one that we can't really address today, and not really in our area of expertise, is the sample prep. But of course, it's going to be a good one. There's an old adage of garbage in, garbage out. So if you put a lot of really bad samples in any system, in any kind of device, it's going to cause problems down the line. So we're going to, of course, recommend working to ensure the sample prep is as good as can possibly be accomplished. But I think what we'll also show is that in some cases where sample prep may not have been as quality as you hoped, we have some really interesting ways of overcoming that. The few that I'll mention right off the top, though, non-representative sampling. Of course, if you have an inhomogeneous sample and you only sample from a single location, it's not going to accurately reflect the overall material. That's a really important point and must be considered when sampling for particle analysis. Also, particle analysis, sample division. So if a sample is too large for an instrument, or it's insufficient or incorrect in its division, this can produce subsamples with different particle distributions. So you got to be really careful when loading samples to be sure it's going to be properly divided out and easily understandable. You don't want to have a lot of clumping and a lot of problems, which would lead to something like the next one, where if moisture is introduced into more of a dry powder situation, a sieve is going to really have a lot of problems with this. It's going to cause a lot of clumping, skewing of size distributions, and especially with some of the laser or light diffraction and scattering systems, really could cause some problems there. So obviously, want to be really careful about how those are prepared. And there's the last we'll mention. There's so many more, of course, but sample contamination, just faulty equipment, insecure storage, user errors, or anything that may lead to the sample doesn't have a representative content that will lead to making it more challenging and getting accurate results in the end. Okay, so it goes without saying, even though I said it, sample prep's really important, and it's something that we should all be considering. However, let's go to the next slide and let's talk about particle analysis challenges, specifically for microscopy. And what we've seen is, say, the top 6 challenges customers have come to us with, where we've worked with them to overcome these using deep learning methods. The first one is debris mixed in with the particle images. And with some methods of microscopy and digital imaging, this can be really a challenge. It can really cause some issues. You may have some types of debris that completely obscure the particles that you're looking for. They may cause challenges with the way that they are, outlined, and any kind of, let's say, machine learning based or histogram based methods may throw off the intensities of the pixels that the particles are being represented by, and it's going to give you inaccurate results. It's been a challenge for years. So debris could be a big issue. Poor edge contrast could be another one. Bright field is notorious. Electron microscopy can be even notorious, where you have just a lot of grayscale values. And because of this, the particles kind of blend in with the background. They have very low contrast edges, or everything's just the same gray value. It makes it really challenging for certain kinds of software, let's say, to distinguish the object. Particles that may be out of focus. If you're in suspension and you have things that are coming in and out of focus, it may be kind of challenging to not pick the blurry ones, the ones that might be in a different focus plane. It may cause issues with picking more than one object, and your objects end up being larger than they're supposed to be, so your particle size ends up being skewed. So we've seen this quite a bit as well, where the out-of-focus particles are being counted, if they don't want to be, should they be, and questions there. Aggregates and clusters. So I have a lot of primary objects, primary particles that are grouped together. There's moisture, or there's some kind of aggregate or agglomeration that is there on purpose or not, and we want to understand how that impacts my sample. Different size particles in the field. Maybe I want to look at the small particles. Maybe I want to look at the big. Maybe I want to look at everything in between, and I want to get different percentages of 10, 50, and 90% size across my entire sample. It could be kind of a challenge. Sometimes the larger objects throw off my measurement, my smaller, and vice versa. And last but not least, our number 6 most common particle analysis challenge that we've heard is densely packed objects. So everything's really close together, they're touching, they're overlapping, they're so close that sometimes whatever method I'm using, they might end up combining multiple objects into one. So I don't know if these are the ones that you've come across. If you've come across others, we'd love to hear from you. Please reach out to us after the webinar or even ask questions at the end. We'd love to know if you think there's more than these 6 challenges, what they are, and we'd love to maybe have a future webinar where we address some of them that we haven't addressed here today. But we'd like to get into these 6 and talk about how we could use AI deep learning as a solution for these different challenges. As a primer to that, we're going to be using imagepro AI, and one of the things that we've done with imagepro AI is introduce what we're calling the neural engine. This allows us to bring a solution to the table that may not be available in other packages or may not be available as open source capabilities. We pretty much have created a tool that combines many different deep learning architectures into a single, simple interface that has a consistent workflow. There's a lot of types of AI models and architectures on the market. I'm sure you're working with things from Google and from Apple and from Amazon and from, wherever it may be, ChatGPT and who knows what it is, all kinds of AI, large language models. You might be working with convolutional neural networks, but whatever they may be, the AI revolution that's kind of going on right now produces a lot of different options. Some of the ones we've seen for convolutional neural networks, which are based on image recognition and object recognition in images, are things like UNet and StarDist and CellPose. These kinds of architectures, whether you're familiar with them or not, are under the hood and available in imagepro. There's a lot of others out there, but we felt like we didn't want to go too far and pick too many because then it would cause confusion as to which to choose. So we picked what we thought were the best ones for the neural engine. And we made sure they were secure and confidential, that when you're using the software, it's on-prem, so nothing being uploaded to any cloud systems. You're not giving away your proprietary images to any company. They're all local for your organization. Everything becomes very user-friendly and consistent because the neural engine provides one interface for all the different architectures. It gives you superior outline accuracy, and as we'll talk about in a little bit, it allows you to streamline the workflow in what we call a protocol. All of these combined into the neural engine. So the way that AI deep learning works, though, is each of these architectures offers you a couple of different options. You can sometimes, with AI that's available in the market, open source, wherever you may find it, they're going to ask you to start with training. And the most common for many years now has been train what's called models, which represent your data, giving it ground truth information. In other words, you get an image, you draw some outlines on it yourself, you give it to the convolutional neural network, it processes it, understands that this object I outlined is the thing that I'm looking for. Then you give it more and more and more of these. I'm talking thousands potentially. You got to do quite a bit of these. It takes a lot of time. It's a lot of difficulty. It's on the difficult scale on the left. Now, if somebody's already done this on your behalf and you go to what's called model zoos, but basically big libraries online, there's a lot of models that are available. Some universities have put these together and nonprofits have put these together, and they make available these models for you to download and use. However, you have to navigate those and you have to understand what was the original data that it was trained on and will it work for me? So it's less difficult, but it is time consuming trying to find the right models. Predicting and fine tuning, less difficult because basically you're using one of those models, let's say that's already been trained, and it can do what's called prediction. It can find the objects in your image that may look similar to the ground truth it was trained on, but it gives you the extra option of then fine tuning. In other words, you're doing training just like was originally done, but you're only doing a little bit of it. You're training on just a few objects, a few particles that didn't quite get picked up, and then you're retraining the entire model so that the next time you run it, it will find everything. And the least difficult is something that's just perfectly designed for you. Your images, your particles, everything is just spot on perfect. So prediction with pre-trained for a specific image and application. So this is kind of what you'll see in the market when you're looking for different AI solutions. So which one do you go with? And what we decided, at least here at MediaSci, is that we wanted to do all of them. So inside imagepro, you have the option of starting with training. You can use external models and import them from different libraries. We can offer fine-tuning after you've run prediction. And of course, we've created quite a few pre-trained models that are ready to go right from the get-go. Since we're talking about materials and particles today, we just want to highlight that we have launched 5 pre-trained models, which are excellent starting points, and they're incredibly versatile. So we work with different grains, such as titanium, in both 2 different phases. We have a versatile grains model, versatile particles, pick up tons of different types of particles and grains. More that are specific with types of metal analysis with something called Widmanstatin patterns, which shows that there's a bit of a striation pattern here, and those patterns can be picked up, not just blob-based kind of objects. It also stretches the boundaries to show that electrospun fibers and even ceramic and glass fibers can be found. So again, kind of that elongated object, if you will, or particle, it's also available. And all these are excellent starting points to just hit one button, does the pre-trained segmentation, and then you're able to find everything you need, potentially even adjust it after the fact. If you're wondering why these types of methods, well, quick example of a super challenging image. It's not a particles based, but it kind of demonstrates that sometimes those life science images are really, really hard because they're not very defined. Here's what these things are: mitochondria in an electron microscopy image. And anyone who knew what they were looking for here might even still have trouble finding all the mitochondria in this image. With a machine learning based method, it's nearly impossible. But if you trained an AI deep learning model to say find mitochondria, it actually does a phenomenal job. Despite the fact that there's so many gray values that all look the same, there's very low contrast, it's messy, there's a lot going on here. AI models have the ability to recall and look for a discrete object, an instance of an object, similar to how the human brain does it. And so it really produces much more accurate results. If it doesn't, as I mentioned a minute ago, maybe I find a couple of objects that are these blue ones, I can just label what was missed, and then when I rerun it, it's actually going to find everything. So with that, I wanted to kind of transition over to Tom and let him demonstrate for you a couple of different things. We want to show you how we could start with pre-trained models, and those pre-trained models can find things that we're looking for, specifically the types of particles that we outlined earlier, and the challenges with them. And then we want to also talk about how we can fine-tune, save, and share those models so that a colleague can use them, or we can set them up at a machine where whoever it is who sits down can run it over and over again, and they're going to have consistency. So we want to look at how it works for these particular particle analysis challenges. Let's start with these first 3, which is debris mixed into particle images, poor edge contrast, and particles that are out of focus. And after Tom gives a quick demo of that, we're going to jump into the last 3 for aggregates, clusters, different sizes, and even densely packed. But let me take it over to you, Tom, and let's talk about these first 3.
Excellent. Thank you, Nick, and welcome, everybody. I want to start with this image here. These are dried droplets on a slide taken by way of bright field imaging with a slight sort of pseudo DIC contrast. And I can actually tackle 2 of the common errors using this single data set. You'll notice that the droplets themselves have very low contrast. We have some that don't have this halo or ring on the outside, and then some of these larger droplets have a sort of ring or gradient on the outside. We also have some debris, and in this case, this debris is actually fully over top of a single droplet. So there's 2 challenges here, and I want to start by highlighting something that Nick mentioned, and maybe something that you're currently using to try to segment objects within your images, and that is using other segmentation methods outside of AI deep learning. So one method is threshold-based segmentation, and this is just looking at intensity values in pixels and we can certainly clip this histogram and find the darker objects or the lighter objects. But because this image is challenging from a contrast perspective, and also just shading issues on the outside that present some sort of vignetting, you can see that I'm not able to accurately identify all of the particles in this image. I'm also picking up the debris as well. So threshold segmentation would not be a good option, but a more advanced segmentation would be machine learning, which we call smart segmentation. With this, I can simply draw regions of the objects that I'm interested in and also draw regions around the background. And I can start to improve this recipe by drawing additional regions. But again, this is still going to present a challenge just based on the lack of contrast with these droplets. So now let's take a look at AI deep learning. And again, we'll start with a pre-trained model here. I can go into my model library, go through it, find one that represents the types of objects that I'm trying to outline. So in this case, we have two that may work. We do have a versatile particles model that's been trained on a lot of different particles, but we also have one called general objects. And this one has been trained on everything from coffee beans and soccer balls, some life science objects, some materials objects. It's a great versatile model that can be applied to just about any image to find blob-like structures within that image. So here I have this model open in the prediction panel, and I'm going to set my size guide to be somewhat representative of the object diameter of what I'm trying to find within the image. So let's go ahead and apply this model to the image and see how well it does. And you can see without any additional training, it's done a decent job of picking up the droplets. Certainly this large one here, you can see it's starting to find the perimeter. It's also, to a certain extent, ignoring this debris that's in the field. So what we can do from here is clone the model and just give it some additional training and label things the way that we want the model to perform in the future. So I can clone this model, and we'll call this one debris model. So the nice thing about AI deep learning is that you follow the same exact process in terms of starting with a pre-trained model, cloning and giving some additional information, regardless of what you're trying to accomplish with that model. It could be droplets, this could be EM particles, could be life science based. It makes no difference. You have to follow the same exact process for each model in terms of training. So from here, all I need to do is delete things that it's found that are incorrect. I can alter labels and I can draw new labels. So we have common tools like a paintbrush tool, polygon tool, but I've already saved several of these labels just to speed up the demonstration. So let's go ahead and add the correct labels into this image. So you can see before it was cutting this droplet in half because of the debris in the field. I've just created a new label that accurately outlines this droplet. Once that's done, I can add this into my training set, click on train, and in about 20 to 30 seconds, I have a brand new model that I can test out on this image and other images within the sequence. So it's a very fast process and a very simple process to develop something very custom to what you're trying to accomplish. Now that that's done, I can open it back up into this prediction panel. And let's go ahead and run this again and see how well it does after just one round of limited training. And here you can see now it is ignoring the debris in the field. It's also doing a great job of finding the outlines of the droplets, even though we have very little contrast. So we've overcome these two common errors, low contrast and debris, in a very short, simple process. So going back, you'll notice with this image, I'm not finding some of these smaller particles. And that's because when I went through training, I was ignoring these small particles. But AI, we can actually take multiple different paths. AI is going to update based on what I've labeled. So this is something where we can actually overcome the contrast challenge, the debris challenge, as well as differences between size. So if I go back, let's start from scratch. I'll run this general objects model again. And what we'll do is clone the model and then start to add additional labels to include some of these smaller droplets. So I'll clone this and we'll say small and large droplets. So here you can see I'm labeling some of the smaller objects as well. So I've also cleaned up the outlines on these large objects to overcome the debris issue, but now I've added some smaller droplets as well. So once this is finished, again, we'll go ahead and apply this new model to the image. And you'll see that we don't always, we can essentially choose the path that we want to go down. We have many different options. All we have to do is just label things the way that we want the model to operate in the future. And so you can see it's starting to find some of these smaller droplets as well. And to be fair, because I've trained this model on this image, what I can do is move to another image that the model hasn't seen. I could go ahead and press count. And you can see it's starting to overcome some of these challenges. So moving on to the last error or challenge that you may come across. Here I have some out of focus, some in focus and out of focus particles. And they have varying degrees of being out of focus. So following the same process, again, I'll just load one of these pre-trained models. I'll start with general objects. And we'll run this prediction without any additional training. So you can see that this model has never seen this image, and it's doing a pretty good job of finding these objects. But there are some errors. So again, we have different paths that we can go down when it comes to model training. I can train this model to find, to a degree, all in focus and all out of focus particles, or I can be a little bit more discrete and I can train this model to only find the in focus particles. So let's go ahead and load something that I've already worked on. So here we have a model that's been trained to find all particles. Again, I would go through that same process of just adding a few more labels, giving it some more information, and then improving this model to find all in focus, all out of focus. But what if I want to be discrete and only find the in focus particles? So something like the out of focus and in focus could be good if you're looking to find a count of the number of particles in the image. But for something like area information, we may not want to include some of these out of focus particles. It could skew our data. So let's go ahead and use this out of the discrete model where I've only trained this to find in focus particles. So through my training session, I would just delete some of these out of focus particles, train it based on those labels, and I would have a result that is a little bit more refined in terms of only finding those objects that I'm interested in. So you can see previously it was finding some of these even slightly out of focus objects, but now it's only finding the perfectly in focus objects. And again, this is just based on my training. So I'll move to another image in the sequence. Again, we'll run the count. And you can see it's a very repeatable process. Based on what I've trained it to identify, it's doing a great job even on images that it has not seen. So those are three challenges that you may come across. Certainly low contrast is something that we see quite often. Debris in the field, again, based on sample preparation, sometimes it's unavoidable. You'll have debris in your images. So AI is able to overcome all of that, plus any images where you may have in focus, out of focus particles. All right, and with that, I'll hand it back to Nick.
Okay, so just for a really quick handoff back to Tom, we just want to make sure that we are identifying what it is that is our next demo. And really, that's simply understanding when we have aggregates and clusters. And that may be because of the challenges we mentioned earlier in sample prep, but it also may be intentional. Number 5, different size particles in the field. And what we've seen a lot is actually when it comes to trying to work with a particular type of approach for this, vastly different objects can cause lots of issues for software in general. And so that's something that now I think we'll be able to demonstrate how that can be overcome. Lastly, densely packed touching particles, probably the most difficult, truthfully, where you actually have so many objects so densely connected that it's hard to find that differentiation. One of the previous ways of doing this would be splitting techniques, where you're looking at watershed type splitting, but that can be really challenging for certain types of images. And so a new approach is definitely needed here. So in our first 3, we looked at kind of contrast and focus and things that are in the way. These last 3 are really a little bit more difficult and probably more like what it is you're coming across. So let's see if Tom can show us how these 4 things, which are very similarly related in the way that you solve it, can all be overcome just by simply using AI and training models, just like we did. So we'll try not to do that and go over it too many times, because it is a very repeatable process that just solves with the same process. But I think with a few different images, we can probably show this in a live demo. So right back to you, Tom.
All right. So like Nick mentioned, it is a very repetitive process, which is actually a good thing. Again, we can accomplish many different things by using and understanding that one simple process of fine-tuning a model. So here I have some powder particles taken with an EM microscope, and you'll notice that we have some of these clusters or aggregates in here. So you may want to take several different approaches when it comes to segmenting these objects. One approach could be finding all of the small particles, even the ones within these clusters. One could be only finding the clusters and maybe running a secondary model to find the smaller particles within those clusters. Another approach could be training a model to find the small particles, but then also finding just the large clusters as well, and not counting the individual particles that make up the cluster. So again, it all depends on how you train the model. So one approach could be only training this to find the cluster. So again, I would have started with one of the pre-trained models, maybe versatile particles. Then I would clone it and give it some labels that are only outlining these large clusters. Now, with all of these images, the training has been done on a single image, or maybe a small region of interest within a single image. So AI deep learning updates very quickly. Now, this does depend on your images and the types of objects that you're trying to outline. But what we've seen is for most applications, you can work with a single image or maybe 1, 2, 3 images. It does not take hundreds of images and tens of thousands of labels to update a model to find your objects accurately. So after this has been trained on one single image, I can apply this to the model. And you can see it's being discrete. It's only finding these clusters. Whereas if I were to run the general objects model or the versatile particles model, it would find a mix. So let's go ahead and try that really quick just to give some context. So the out-of-the-box pre-trained model, I'll go ahead and click on count. And I can tell you it will do a very good job of finding all of these smaller particles in the background and a mix of the small particles within these clusters. So it's a great starting point. We don't have to start from scratch. We don't need to label every single particle. In this case, we just have to delete some labels that are incorrect. But let's assume I want to find all of the small particles, which this model is doing a great job of. But I don't want to find the small particles within these large clusters. Maybe I want to count them as one single object, and I can do a classification, and I can classify clusters and small particles. In that case, again, I would clone the model, give it some new labels. And after that's done, we can apply this to the image. I have my size guide set a little bit too large. There we go. So you can see it's finding the small particles, but instead of finding the small particles within the clusters, it's now counting these clusters as one single object. And this is based on what I've trained it to do. Now, one thing I had mentioned is classification. So we do have options to classify by a single measurement. So this could be area-based. We could use some sort of texture-based measurement, depending on what I'm trying to classify. But the most simple form of classification would be this classify by measurement. So here I could set ranges. I could spread things out evenly. I can give these class names. I could call this small and large. And now I can classify based on one single measurement type. Now, we'll showcase protocols at the end, but I had mentioned that you can train several different models. So we could train a model to just find these clusters and then run that secondary model to find the smaller particles that make up the cluster. So it is possible that, depending on what information you're trying to extract from your images, you may train several different models that can all be included in the automated workflow. So moving on to the last challenge, which would be densely packed particles. This image actually represents a lot of what we've already gone through. So you can see that we have some small particles, some large particles. You'll also notice that we have many different types of particles, some that could be classified as debris, certainly different types of textures and intensities throughout this image. So following that same process, let's go ahead and just open a model that's been trained based on the versatile particles model to identify all of the particles within this image. And then we'll go through a more complex classification. So after some additional training, initially this would not have picked up the larger particles in the image. It would only have picked up the smaller or just the larger based on what I've set this object diameter guide to. But now that I have a model that's working, I can go ahead and classify these objects. And because this is a more complex classification, I can't just use area or diameter to classify all of these objects. I can use what we call a learning classification. So I'm going to change the outlines just so it's a little bit easier to see what's on the inside of each object. And then what we'll do is go through the types library here. So imagepro includes a very large library of measurement types that are available to you. So in this case, because I have a lot of different measurements that could really be used to classify, all I have to do is just add the ones that are relevant into the selected measurements, then we can do a learning classification. So in some cases, area does make it is an identifier when it comes to classifying. But I think with these objects, we may want to use some texture-based classifiers. So I will add clumpiness, heterogeneity. We can add margination. We could include some intensity-based classifiers, some density-based classifiers. All of these can be used to accurately classify. So we'll start with these. And let's open up learning classification. So if I zoom in on my image here, just within this small region, I have several different types of particles. I have some that have a texture to them. I have some that are very light, and then I have some that have the same sort of grayscale values throughout the object. So let's go ahead and add several different classes. So class 1, I will call this light objects. Class 2, let's call textured objects. And class 3, we can call them dark objects. So now what I'll do is I'll choose all of the relevant measurement types, and I'll choose area, heterogeneity, clumpiness, margination, and integrated optical density. So now all I have to do is select a few reference objects within each class. So I'll start with light objects, and I'll just highlight a few light objects to give the classifier some information. Then I'll highlight a few textured objects. And lastly, we can highlight some dark objects or uniform objects. Once that's done, I can click on Classify. And based on the reference objects that I've given for each class, you'll notice that it's assigning a weight. In this case, heterogeneity is actually the highest identifier when it comes to classifying these objects. So again, sometimes we may want to take the route of finding everything, training a model to find every particle within the image, but then we can use classification, whether that is a simple single measurement type classifier or a more complex learning classification by combining multiple different measurement types together and pointing to some reference objects. But in either case, AI deep learning is the method that can overcome all of these challenges when it comes to segmentation. AI deep learning is the starting point, and then we can use other tools like classifiers and combine this all into an automated workflow that we'll show in a minute. All right, and I'll send it back to you, Nick.
All right, great. Thanks, Tom. So this is a really exciting solution to a lot of the challenges that we talked about a moment ago. And what we can now do is demonstrate that all 6 of these challenges can be overcome with AI deep learning. And everything that we just demonstrated is really just a couple of steps in a larger workflow, really just the segmentation step, the identification of individual particles, and then, as Tom just showed at the very end, classification of those particles by choosing different types of measurements to weight automatically and divide all the particles into the bins that you may want. But there is one more thing we really need to talk about. However, we wanted to just stop right here to say one of the advertisements that we had was to solve all 6 of these problems in 1 hour, and we're right at that hour mark. So what we're going to do is we're now going to transition into a short secondary discussion, which is now that we've solved those 6 problems, how do we do this in an automated way? And how do we do this to maintain accuracy? So we just have a brief demo that would demonstrate for you how we can now take this one step further. AI deep learning is definitely a technology that is allowing us to very accurately separate the objects. You can see it visually, so you have that confidence that the type of QC you're doing is truly getting the right results. But throughput's important. So how am I going to automate this, make this a little faster, make this more repeatable, make it so somebody can do this on my behalf and I can just set it up and someone can run it. Let's talk about that really quick. So imagepro being the end-to-end solution, you could set this up 2 different ways. The first way you could set it up is we could use imagepro for the import process, measure, and report process end-to-end instead of just what we demonstrated a moment ago, which is just the measure step. So the measure step is everything we've talked about up to this point. If you wanted to make a more end-to-end solution, imagepro does support over 150 digital cameras. We work with OME.TIFF and open and import those types of images. We also import and build any kind of image you may have from any kind of file format. And of all the proprietary formats from microscopy vendors, we support over 65 plus formats. If you didn't want to support a digital camera, of the 150 we have, a number of them, as you see on the screen here, would work with any microscope. plug it in, download from our website the driver and the manufacturer's driver, and you'd be able to see live images of your particles right in imagepro, snap an image, and then immediately go to the next 3 steps. We do kind of streamline this a bit by working together with Hitachi High Technologies. They have a send to imagepro button on many of their SCM systems and in their software to make it really easy transfer if imagepro is installed locally. We also work with all the other file formats from all the other electron microscopy vendors, and we do the same thing on the optical microscopy side. And you may have seen advertisements with special packages that are available between us and Modic Instruments in the Americas right now. And you also can work with really anyone, Zeiss, Evident, Leica, Nikon, and more on the optical side as well. And so once those images are into imagepro, you can adjust your lookup tables, you can stitch and tile larger areas if you don't want to work with just the small area that's in the field of view. If you need to do any kind of adjustment for stacks or extended depth of field because maybe your objects might have be slightly larger than that field of view, we can do processing in that way. And as an example here, these aren't particles, of course, but these are a fiber image where I am able to see on the left-hand side maybe some tiling artifacts of a larger field of view where the shading's not quite right. imagepro can do processing to actually correct for that and stitch and tile quite well. On the measurement side, more than just particle analysis is possible. So if you wanted to use it for other types of applications, such as layer thickness, you could do that. And of course, particles have been talking about today. Now, once we've done all of this, the last thing is that reporting. And so we want to look at data tables with statistics and graphs and everything I need to put together a report to understand very easily whether or not the particles I'm working with have passed or failed some kind of quality test, or just generally the material is meeting standards. So these 4 steps are something that we want to be able to automate, want to be able to do more rapidly. So we want to talk about streamlining these steps with what we call a protocol and also batch processing, pointing a protocol to an entire folder full of hundreds or thousands of images and doing this in a rapid process, then producing custom reports on the outset. So imagepro comes with what we call analysis protocols, which are a multi-step process. The first step is going to be that segmentation we've already discussed. Then you can also classify, and then you can analyze. And so you're just going to get a 3-step or 4 or 5, 6-step process, but it's going to be those same steps over and over again. Helps you standardize with guided steps. It integrates all the AI technology we've talked about. It'll give you easy access to a bunch of custom reports we've already created. They'll just automatically be created, or you can customize your own. And that protocol is already batch ready. If you'd like to work with anything that's already been created on the bright field or electron microscopy side, we have composite materials, fiber separation and thickness, grain size, layers, particle phase, particle size, phase, pores, and Widman-Staton patterns as already existing protocols that you can just run right out of the box in imagepro, or you can customize these yourself to create something for your organization. So with that, let me hand it off to Tom. Let's just quickly go through how we'd set up a protocol, look at some of the ones already available, and how easy it could be to make everything we just talked about a little bit more automated so that it really gets you back some time that's really valuable and makes this repeatable regardless of who it is that's using the system. Go back to you, Tom.
All right. So thank you, Nick. We'll tie everything together with protocols. So what we've gone through so far is just the segmentation step. We've just used AI deep learning to find whatever object area or pattern we're interested in finding. Now we need to tie everything together. Maybe we need to add classification steps, but ultimately you'd be interested in extracting data from your images, and who doesn't like a very automated workflow? So if I open up our protocol library, again, we have many different protocols. These are essentially just templates. They can be fully customized, but they're great starting points. And they're also very easy to follow. It's an interactive workflow, everything is guided. So this is actually a very intuitive process. So all I have to do is go through my protocol library here, and I'm in the materials collection, and I'll go through the library and pick one that makes sense based on what I'm trying to accomplish. In this case, using this powder particle image, maybe I want to get some size information, whether that's area, circularity. I'm going to choose our particle size analysis protocol. So we have two versions. The first version just by default goes to another segmentation method, whether that's threshold or machine learning. And then we have an AI-powered version that's going to, by default, point to one of the pre-trained models. All I have to do is click on Load. And I have this initial setup panel here. I can sync to my image. It's going to recognize, is this a monochrome image? If it's a multi-channel fluorescence image, imagepro automatically recognizes the image type, the file type, and it will also import any metadata, whether that's a calibration or other metadata information. I can also point to a calibration. If it's not importing that metadata, I can certainly create a calibration within the software and point to that in this setup step. Now, we always start in what we call interactive mode. You'll see I have two steps, and ultimately I have my results panel where I can configure what measurement types and data are output. But I just need to follow the prompts and make changes to any of the settings along the way. In this case, step number one is segmentation. It's pointing to the pre-trained general objects model, but because I've already trained another model to expand what it's finding in terms of size, small particles, large particles, I'm going to point to that model that I've cloned and trained. So once I do that, I click on OK. It's going to segment, find all of the particles, and then I have a couple segmentation options that I can change some of these settings. So the first setting is setting some sort of measurement threshold. Again, if I need to get rid of objects based on any measurement type, this could be area, circularity, I can do that in this step. Although with AI deep learning, because I've trained it to only find the objects that I'm interested in, we actually don't have to use this area threshold or measurement threshold much. I do have this option to select clean borders. And in this case, if I am interested in area measurements, I don't want to count any particles that are split because they're touching the perimeter of the image. So I have clean border set to all, and you'll notice that it's not counting, it's excluding these objects that are touching the perimeter. Here's where I can also choose my classification type. I can go off of that single parameter classification, or I can load one of the learning classifiers that I've already created. So we will load the classifier that we just did in the last demonstration and click on Classify. So in the final step, this is where we have our data output, and we can make some changes and choose some options with the goal of fully automating this process. Maybe we need to batch process an entire folder full of images. In that case, I can automatically create a report. Maybe I want to use one of our predefined report templates. We do have templates for every single protocol. So in this case, I'm going to use the particle size multiple sites, which includes additional graphs if you'd like to track changes throughout the batch. And maybe I want to automatically export results into an Excel spreadsheet. So I'll choose these options. And if I need to, I can define additional measurement types. So every protocol is slightly different in terms of the data that's output. In this case, I do have some high-level statistical information. I have a total object count, D10, D50, D90 values. I get some mean, median, and standard deviation information in terms of area. I can also look at class statistics. So because I've created these three classes, maybe I want to look at values within each of those classes. This is all predefined with this specific protocol, but if I need to, I can choose types and I can change any information. I can change the way that the data is output. Once that's done, I'm going to save a version of this that I'll call particle size with classes. So now I've walked through that entire process. I want to repeat that process on a folder full of images. So I'll click on Finish, which takes me back to the beginning of the protocol. So I'll delete all of the measurement data that we acquired while walking through the protocol the first time in interactive mode. And what I can do now is uncheck interactive, and I now have the option to either run that same process on a single image, or in this case, the sequence. I do have 3 images included in this collection. Or I can run a batch. I can point to a folder and choose as many images as I'd like and go through that same process. Now, because I have the sequence, I can just choose Run Selected, and it will apply this to all 3 images within the sequence. And because I have chosen to export results to an Excel spreadsheet, as well as create that custom report, it's going to fully automate my data output as well. So now that it has run through this process, you can see I have my custom report. The reports can be customized as well if you want to include additional charts, but it does include graphs for mean diameter versus the number of objects counted, D10, D50, D90. This gives a nice visual representation of major changes that may take place throughout your sequence. I also have, again, the summary table, statistical information on the entire count throughout the images. I can also look at statistical information for each image. If I need to include individual measurements into this report, I can do that as well. And then I can look at the Excel spreadsheet. You can see here I've got a snapshot of each of the images, and I have all of my data compiled. So this, again, is the same process. You start with one of the pre-made protocol templates. You go through this in interactive mode one time just to set up your specific parameters and maybe point to AI models that you've trained. And now you have something that you can recall at any point. If you need to come back to this type of analysis, it's already stored in your protocol library with all of the changes that you've made. So now we just have to click a single button and we can automatically analyze and export that data. So this is a single model type protocol. I've just applied that one model that we created, but I do want to go back to the aggregate image here. So I had mentioned that we could go a couple different directions. We could train a model to just find the clusters, and then we could train another model to find the smaller structures within. So we do have additional protocols. We can customize the particle size protocol, or we can use one that's already set up to do this type of analysis. So we have this essentials collection that includes this objects within objects. So with this protocol, we have a parent object. So what I'm going to do is I'm going to set this to clusters. And then we'll set a child object, the small particles within those clusters. So this is where throughout this protocol in steps 2 and 3, we can actually use 2 different models. So in step number 1, let's go ahead and point to the clusters only model. We want to set this as the parent region. I'll click on count just to make sure that this model is working correctly. And you can see it is. It's finding just the cluster objects. I'll make sure I have my range wide open. I don't want to discount anything based on area. Now in the secondary step, it's pointing to another pre-trained model, general objects. But now I can use any one of these models, and actually let me point to just the general objects model. That does a pretty good job of finding the small particles. So now you can see I have a perforated line around what we found in the first pass, which was the parent objects, the clusters. Now when I apply the secondary model, it's just looking within the cluster regions. It's ignoring everything on the outside of the clusters. And so now I can get information based on all of the smaller particles within each of the clusters. So this is a way that we can apply multiple models within a single protocol. And you can add more than one. You can have one parent and you could have 6 child objects. So you could run 6 different models within the protocol. They're extremely flexible. We don't limit you based on the templates. You're not trapped with just the steps that we've come up with. You can fully customize these to add additional steps and some more complex features as well. So from start to finish, that is how you can accomplish automating your workflow.
Great. Thank you, Tom. All right. Well, I'm really excited to show that we were able to accomplish all 6 of the challenges and maintain the automation that is necessary for keeping up your throughput, allowing you to easily switch between users. So hopefully what we've demonstrated today is that there are ways using AI deep learning to resolve some of these challenges. And if you do want to give imagepro consideration as a solution for this, there are a number of things that do make it unique, such as using AI deep learning for that superior outline accuracy and the user-friendly operation, as we demonstrated. Everything's on-prem, so it's secure and confidential. The protocols are ready for using AI. The protocols are guided steps to really make it easy to walk through and not have to know what to use and which tools when. AI is fully integrated and the protocols are batch ready. Each one of them gives you an instant report and really tries to tie everything together nicely. If you'd like to, we're happy to discuss with you some next steps, such as considering imagepro AI for materials as a package. We bundled everything together in one nice, neat product that allows you to have the AI deep learning segmentation, all the pre-trained models for materials, all the protocols in the materials collection. What we didn't show today was it would also include manual measurements. So if you want to do point-to-point or hand-drawn measurements, and if you don't need automation for any particular moment, that's available to you as well, including all of the image display capabilities, processing, and more. So imagepro AI for materials is a fully bundled package. It also can come with some assistance. And so one of the things that Media Cybernetics likes to offer is what we call success plans. Obviously, getting started with any new software is something you want to take seriously and try to make sure you learn it as quickly as possible to maximize your investment. We look at success plans as our way of working together with you and collaborating on your success. You can start with a standard plan, which just provides onboarding and technical support for a year. We can have professional plan available that would have everything in standard plus software upgrade protection, meaning every year we release new versions and new capabilities every year. You'd get all of those included at no additional charge. You'd also get access to any new models or protocols that come out throughout the year. And so because of that, you would have always the latest and greatest, which can be really beneficial as our models are always improving and helping you to get started more rapidly. Our most popular actually is our ultimate plan, and that allows you to have everything in standard and professional, but also uptime guarantee. If you ever need a few more licenses or have to have your IT department change something, we're going to provide you licenses, no questions asked. You get license server support if you'd like to distribute and float licenses over a number of different computers. We'll provide software training hours, application service hours, and even if you're having trouble with model training, training as a service. So we offer these different success plans to allow you to have peace of mind, and we offer them in 1 or 3 year plans. Everything is live but also remote. So we'll provide our services to help you really stay on top of any new projects that come up, and we make it really affordable. There's some out there that are offering something like this for over $10,000 a year. We think that's way too expensive. We're offering ours for a very small fraction of that, trying to make sure that you can always have training available to you, new users get up and running fast, you have new features as available, and you're working with Media Cybernetics to really maximize imagepro for particle analysis, quality control, and getting great solutions in the end. So that concludes our webinar for today and all the content we have for you. We are happy to stick around for a few more minutes. If there's any questions, you can use the chat and we'd be happy to answer those. But thank you so much for joining. And if you don't have any questions, just thank you for joining us, and we appreciate your time today. So if you have any questions, we'll hang out for a few minutes and we will be happy to answer those. So I will stop sharing for now, and Tom and I will check the chat, and feel free to throw any questions in there, and we'll do the best that we can to answer. Just a quick question that came in here, Tom, which was, in the last demo that you gave, is it part of the package for you to be able to handle selecting the larger objects, but also to then measure inside of them for what looked like smaller children objects in the clusters?
Yes. Yeah. So the imagepro AI materials package includes everything, and the ability to customize protocols, and it includes features that we didn't go through as well. But yes, you would receive all of the pre-trained models, the entire materials pre-trained model collection, as well as the entire materials protocol collection. So you can start with one of those essentials protocols, that objects within objects protocol, and you can make changes, but you can also create your own protocol from scratch. Again, it can include as many different steps as you'd like, as many different options within each step. So yes, it is all included. Everything that you need to do just about any type of analysis for materials comes with the AI materials package.
Thank you, Tom.
So somebody has asked if you already have imagepro 10 and you want to upgrade. So we actually do have an upgrade option to go from any version 9, version 10, or even version 11.0 to the latest imagepro AI package. We have upgrade paths that go to the materials package, and an option to go to the life science package. So certainly reach out. We can send you pricing information based on the license that you currently have.
Right. Yeah, thanks everybody for all the kind words. Appreciate it. I'm glad it was beneficial today. Okay, another one, which is there any difference between images that are coming in from an electron microscope versus an optical microscope? Would you use the AI any differently? So
there could be a number of different answers. No, is I think the general answer. That there's nuances to everything. We've certainly come across some applications where Maybe you take a slightly different approach on either the AI architecture that you use, or maybe how you label things. But in general, it makes no difference. I was showing some optical images, some EM images. They could be X-ray images or macro images taken from your cell phone, or some sort of consumer camera. You follow the same exact process when it comes to applying a pre-trained model and then fine-tuning and adding your own labels. So that is the nice thing about AI deep learning. Once you understand that process of starting with a pre-trained, cloning, and adding some additional information, it makes no difference what your images are. You could be looking for zebra in the wild. You would use this same exact process to fine-tune and label the zebra, and AI would work. So yes, you can take the same approach regardless of the modality.
And everyone stay tuned for our next webinar on zebra analysis in the wild. So, all right. Well, I don't see any other questions coming through. So thank you so much for your time today. And we look forward to seeing you on a future webinar. We definitely had a few more topics such as fiber analysis and grains that we weren't able to cover today, but we're hoping to have those in a future webinar as well. If you work with those types of materials, that will be down the road. Otherwise, thank you for your time and hope to talk to you soon. Goodbye.